Hello, everyone. In this section of Electronics 1, we will introduce peak rectifier circuits, which are one important diode application. The circuit on the right is the half-wave rectifier introduced in the previous section. If we replace the resistor R with a capacitor, the circuit becomes a peak rectifier. The circuit shown at the lower right is a peak rectifier circuit. We will now analyze the electrical operation of this peak rectifier. Let us begin with the current voltage relationship of a capacitor. A capacitor is a charge storage device. The stored charge Q equals the capacitance C multiplied by the voltage across the capacitor V. Therefore, when the stored charge changes, the capacitor voltage also changes. The charge change, delta Q, equals C multiplied by the voltage change, delta V. For the stored charge in a capacitor to change, charge must flow into or out of the capacitor. That charge flow is current. The charge change delta Q equals the capacitor current I multiplied by delta T. Since delta Q also equals C multiplied by delta V equals 1 over C multiplied by I and delta T. If we integrate both sides over time, the capacitor voltage change equals the time integral of the capacitor current divided by the capacitance C. Conversely, the current through capacitor C equals C multiplied by the rate of change of the capacitor voltage with respect to time. Mathematically, when current flows into the capacitor voltage increases. This is the charging condition. The voltage increase equals the time integral of the incoming current divided by C. When current flows out of the capacitor voltage decreases with time. In the discharging condition, the current is equal to C multiplied by the time derivative of the capacitor voltage. After understanding the capacitor current-voltage relationship, we can start analyzing the peak rectifier. To simplify the analysis, diode D is treated as an ideal diode. It is a short circuit under forward bias and an open circuit under reverse bias. First, before the signal source Vs is connected, assume that the capacitor initially stores no charge. Therefore, the capacitor voltage Vc is 0 volts, and the output voltage Vo is also 0 volts. At t equals 0 seconds, the signal source Vs is connected. Initially, the capacitor voltage is 0, so the cathode of diode D is at 0 volts. After Vs is connected, Vs becomes the anode voltage of the diode. During the negative half cycle, from 0 to t over 2, the diode is reverse biased and behaves as an open circuit. Therefore, no current flows into the capacitor and the capacitor voltage remains 0 volts. Next, during the positive half cycle, from t over 2 to 3t over 4, the diode becomes forward biased and behaves as a short circuit. Therefore, the capacitor voltage Vc follows the input voltage Vs. This voltage is also the cathode voltage of the diode. When time becomes greater than 3t over 4, Vs starts to fall from its positive peak value. However, the diode cathode is still held near the maximum value of Vs stored on the capacitor. Therefore, diode D becomes reverse biased and open. Since there is no current path for the capacitor, its voltage remains at the positive peak voltage, V peak. After that, unless Vs rises above the stored peak voltage again, the diode stays off and the capacitor keeps holding the positive peak value. This is why the circuit is called a peak rectifier. The output voltage is the maximum positive value of Vs. Now suppose we reverse the diode connection in the same circuit. The cathode is connected to the signal source Vs, and the anode is connected to the capacitor and the output node. Initially, the output node is at 0 volts. For the diode to turn on, the anode voltage must be higher than the cathode voltage. Since the anode initially stays at 0 volts, the cathode voltage must become negative for the diode to conduct. Therefore, when Vs is negative at the beginning, from 0 to t over 4, the diode is forward biased and acts as a short circuit. As a result, the capacitor voltage Vc follows Vs. After t over 4, the diode anode is at the most negative peak voltage, negative V peak, while the cathode voltage starts to rise. The diode therefore becomes reverse biased and open. With no current path, the capacitor holds the negative peak voltage. In this case, the output voltage of the peak rectifier is the maximum negative value of Vs. Therefore, the polarity of the peak voltage is determined by the diode connection direction. Next, we discuss a more advanced peak rectifier circuit. As shown on the right, capacitor C and resistor R are connected in parallel. This parallel branch is connected in series with diode D and the signal source Vs. We will analyze the output voltage from the time domain waveform. First, consider the time interval from 0 to t over 4. During this interval, the diode anode voltage is Vs, which is positive, while the cathode initially starts at 0 volts. Therefore, the diode is forward biased and conducts as a short circuit. The output voltage VO is then equal to Vs. After t over 4, Vs starts to decrease. The diode anode voltage becomes lower than the cathode voltage, so the diode becomes reverse biased and open. At this point, Vs no longer affects the capacitor-resistor branch. In the previous peak rectifier without the parallel resistor, the capacitor had no discharge path, so Vc could stay at the peak value. In this circuit, however, resistor R is connected in parallel with capacitor C, creating a discharge current path. As shown in the upper circuit, when t equals t over 4 and Vs starts falling from the peak value Vp, diode D is reverse biased and open. Because capacitor C is connected in parallel with resistor R, the capacitor now has a current path through R. Current flows out of the capacitor and into the resistor. As charge leaves the capacitor, the stored charge decreases, so the capacitor voltage also decreases. Since the output voltage equals the capacitor voltage, the output voltage decreases. This is the capacitor discharging interval. Notice that the diode anode voltage is Vs, while the cathode voltage is VO. During the capacitor discharge process, VO keeps decreasing, and the diode remains reverse biased and off. The diode will turn on again only when the anode voltage Vs becomes higher than the cathode voltage VO. At that moment, the diode conducts again and recharges the capacitor. In other words, at time t1, the diode starts conducting again and the capacitor begins to recharge. The charging continues until time t2, when the voltage reaches the peak value Vp again. Before the recharge begins, the output voltage has dropped by an amount Vr. The recharge interval is delta t, which equals t2 minus t1. Now let us focus on the capacitor discharging curve. As shown in the waveform, this occurs after t over 4 and before the next charging interval begins at t1. Since the capacitor discharges through resistor R, this is an RC discharge process. The capacitor voltage follows the standard exponential discharge relation. The capacitor voltage Vc equals the initial voltage Vp multiplied by exponential of negative t prime over Rc. Here, t prime is the discharge time, and the entire ratio, negative t prime divided by Rc, is inside the exponential function. For a fixed discharge time, a larger Rc product leads to a smaller change in Vc. A larger R reduces the discharge current, so the capacitor discharges more slowly. A larger C means the capacitor stores more charge, so the same amount of discharged charge causes a smaller voltage change. The total discharge time is the period t minus the charging interval delta t. Therefore, at time t1, the capacitor voltage equals Vp minus Vr. This is also equal to Vp multiplied by exponential of negative t minus delta t divided by Rc. In this expression, the quantity t minus delta t is divided by Rc, and the negative of that ratio is inside the exponential term. If the charging time delta t is much smaller than the period t and Rc is much larger than t, then the exponential term can be approximated by 1 minus t over Rc. From this approximation, the ripple voltage Vr is approximately equal to t times Vp divided by Rc. In other words, Vr increases with the signal period and the peak voltage, and decreases when R or C becomes larger. Because the period t equals 1 over the frequency f, Vr can also be written as Vp divided by Rcf. This equation can also be derived in a more intuitive way. Under the condition that Rc is much larger than t, the amount of discharge is small, so the voltage ripple Vr is also small. During the discharge interval, the load current through resistor R can be approximated as Vp divided by R. The total charge lost during the discharge interval is approximately the load current IL multiplied by the discharge time t. Since IL is approximately Vp over R, the charge loss is approximately Vp times t divided by R. The same charge loss is also equal to the capacitance C multiplied by the voltage drop Vr. Equating these two expressions gives Vr equals t over Rc multiplied by Vp. Since t equals 1 over f, this can also be written as IL divided by Fc. After completing the discharge analysis, we now look at the charging interval from T1 to T2. During this interval, the diode becomes forward biased again and conducts as a short circuit. The question is, how long is this charging interval, delta t? For convenience, we shift the time origin so that t equals 0 occurs at the positive peak of the sinusoidal input. Then the input can be written as Vs equals Vp times cosine of omega t. At time t equals negative delta t, the input voltage is Vp minus Vr. Therefore, Vp times cosine of negative omega delta t equals Vp minus Vr. Since cosine is an even function, cosine of negative omega delta t equals cosine of omega delta t. When t is much larger than delta t, omega times delta t is much smaller than 1. Therefore, cosine of omega delta t can be approximated by 1 minus 1/2 times omega delta t squared. Substituting this approximation into the previous equation and solving for omega delta t gives omega delta t equals the square root of 2Vr divided by Vp. The entire ratio 2Vr over Vp is inside the square root. Next, we calculate the average diode current, ID average, over one full signal period. During one cycle, the diode conducts only during the charging interval delta t. The total charge supplied to the capacitor during charging must equal the charge lost during discharge. The supplied charge equals the average capacitor charging current, IC average, multiplied by delta t. Therefore, the average diode current, ID average, equals the average capacitor charging current plus the load current, IL. The average capacitor charging current equals Q loss divided by delta t. Since Q loss equals C times VR, ID average equals CVR divided by delta t plus IL. From the earlier result, VR is approximately equal to IL divided by FC. Substituting this into the equation for ID average gives ID average equals IL divided by delta t times F plus IL. Since omega equals 2 pi f, this can be written as IL multiplied by the quantity 2 pi divided by omega delta t plus 1. Using the earlier result that omega delta t equals the square root of 2 Vr over Vp, we obtain ID average equals IL multiplied by the quantity 1 plus pi times the square root of 2 Vp over Vr. After finding the average diode current over one period, we now calculate the maximum diode current, ID max. When the diode conducts, the diode current splits into the capacitor current and the load current. Therefore, ID equals IC plus IL. Since the capacitor current IC equals C times dVc over dt, the diode current is C times the time derivative of Vc plus IL. Because Vr is small, the load current IL can be treated as approximately constant. Therefore, ID max occurs when the capacitor current reaches its maximum value. This happens when the capacitor voltage has the largest slope with respect to time. From the waveform, this occurs at t equals t1. For mathematical convenience, we again shift the time axis so that the input voltage is Vs equals Vp times cosine of omega t. During the diode conduction interval, the diode is shorted, so Vc equals Vs, which equals Vp times cosine of omega t. Therefore, the slope of Vc at t equals t1 is the same as the slope of Vp cosine omega t at t equals negative delta t. This gives Vp times omega times sine of omega delta t. Thus, ID max equals C times Vp times omega times sine of omega delta t plus IL. Because omega delta t is much smaller than 1, sine of omega delta t can be approximated by omega delta t. Therefore, ID max becomes C times Vp times omega multiplied by omega delta t plus IL. We have already derived omega delta t as the square root of 2 Vr over Vp. We also derived Vr as approximately IL divided by Fc. Using these results, omega c can be rewritten in terms of IL and Vr, and then substituted back into the expression for ID max. Finally, we obtain ID max approximately equals IL multiplied by the quantity 1 plus 2 pi times the square root of 2 Vp over Vr. Now compare the average diode current and the maximum diode current. Since Vp is much larger than Vr, the one term can be neglected. Then ID average is approximately IL times pi times the square root of 2 Vp over Vr, while ID max is approximately 2 times that value. Therefore, ID max is approximately twice ID average. Let us summarize the three important formulas for the peak rectifier made of a diode in series with a parallel RC branch. The ripple voltage Vr is proportional to the input period, which is the peak-to-peak time between charging events. If the input Vs first passes through a full-wave rectifier before entering this peak rectifier, the signal period seen by the peak rectifier becomes one half of the original period. Therefore, VR can be reduced by half. In the waveform, the red input signal first becomes a full wave rectified signal, so the effective period becomes T over 2 before entering the peak rectifier. This reduces the discharge time and the ripple voltage. The result is an output near VP with a ripple VR. If this output is further processed by the voltage regulator introduced in the previous section, the ripple can be reduced even more, producing a stable DC voltage. That concludes the introduction to peak rectifier circuits. Please stay tuned for the next lecture. See you next time. Bye-bye.